Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over Dalton's law of partial pressures. So let's get into this. So the first thing I want to talk about is, what is Dalton's law of partial pressures? Well, that is written right here. The total pressure of a mixture of gases is equal to the sum of all the partial pressures of all the gases mixed together in the same container. So what does that mean? Well, let's start with what we mean by partial pressure. The partial pressure of a gas in a mixture of gases is going to be that pressure which the gas would exert if it was all alone in the container and not mixed with other gases, right? So that's what we mean by partial pressure. So again, partial pressure of a gas in a mixture of gases is just the pressure that gas would exist if it was all alone. Now, that is not different from what that gas would be when it mixed together. So basically, the pressure that the gas is going to have is going to be the same whether it's all by itself in the container or if it's mixed together with other gases in the container. And the reason for this goes back to the kinetic molecular theory, right? So if we go back to the kinetic molecular theory, the assumptions, a couple of the assumptions that we are working with is that, one, the gas particles are mass points or point masses. A point mass is basically a kind of a theoretical mass that has no volume, right? So in reality, that's not the case, but in practicality, we can assume that that to be true because that the size of the particles given the size of the container is going to be so small compared to the size of the container or the volume of the container that we can simply ignore that volume. It's going to be negligible. But in reality, it's not zero. But the assumption, one of the assumptions of the kinetic molecular theory is that we're dealing with masses that have no volume, or what are called point masses. Okay, so that's the first thing. The second thing is the assumption that these particles are not exerting any forces on each other. There's no attractions or repulsions being applied to each particle. They don't affect each other in any way, with the exception of just colliding together. So the collisions are perfectly elastic, and so there's no worries about the particles affecting each other in terms of speeds and all of that stuff, losing energy. So given those two assumptions, then when you mix the gases together, they are not going to affect the pressures of each other. So basically, if you look at here, I have kind of a picture set up. So if we look at here, the gas particles in blue, they're by themselves. So they're going to collide with the walls. They are at a certain temperature. They're going to be at a certain average speed because they're at a certain average kinetic energy due to the temperature. And so here, the speeds of the particles are at a certain amount. And so the particles are going to be colliding with the container in a certain rate. So those collisions are going to apply a force to the container and therefore give a pressure. So these particles are going to exert a certain amount of pressure on the inside of the container. Same thing with these particles. So these particles of this gas in red again, they're traveling at the same temperature. So these guys are traveling at a certain temperature, and these guys are traveling at a certain temperature. Got to fix my picture. So again, these guys are going to be traveling at a certain average speed, and therefore there's going to be a certain number of collisions per second being exerted on the wall, and therefore a pressure is going to be exerted in this container here. Now, if we take these two gases and we put them together into the same container, the only thing that changes here is that they are going to be colliding with each other. That's the only change. So the collisions with each other doesn't affect the amount of collisions that each gas has with the size of the container. So the blue particles are still going to be hitting up against the sides of the container at the same rate because one, they're in the same volume, and two, it's the same temperature. So that hasn't changed. So the average kinetic energy of the particles does not change. So therefore, the collisions, the number of collisions that each particle hits against, has with the container, doesn't change. So the blue particles are going to hit up against the sides of the container at the same rate as before, and the red particles are going to hit up against the sides of the container as before. So therefore, the pressure of the blue particles here and here is the same, and the pressure of the red particles here and here is the same. They haven't changed. So therefore, the pressure exerted by the blue particles in the container is what we call the partial pressure of the blue particles, plus the partial pressure of the red particles added together is going to equal the total pressure inside this container due to both gases. And again, remember, the total pressure of the container inside the container is due to the total number of particles inside the container, right? So remember, pressure is determined by the number of particles, because more particles means more collisions up against the sides of the container, which means more exerted pressure, more exerted force, which means more force per square inch or per area, and therefore more pressure. So because there's more particles here, you're going to have a greater pressure. But the total pressure inside this container is going to be due to the pressure of the particles due to the blue particles and the pressure due to the red particles added together. So if we put that into an equation, you get the total pressure inside your container is going to be equal to the pressure of gas A plus the partial pressure of gas B plus the partial pressure of gas C, and so on, which is equal to the sum of the partial pressures of all the gases into the container. So this, ladies and gentlemen, is Dalton's law. The total pressure is equal to the sum of all the pressures, the partial pressures of the gases mixed inside the container. Okay, so we can relate this to the ideal gas law. So if we take our ideal gas law, PV equals nRT, we can rearrange this to set it up so that we have pressure of a gas is equal to the moles of the gas multiplied by the ideal gas law constant multiplied by the temperature of the gas divided by the volume of the gas. Okay, now let's say that we have blue and red. Let's say that our blue gas particles, that's going to be neon, and our red gas particles is going to be argon. So if we do this separately, so the pressure of the neon particles, or the partial pressure of the neon gas, is going to be equal to the number of particles, or the moles of the neon gas, multiplied by the ideal gas law constant, multiplied by the temperature of the neon gas, divided by the volume of the neon gas. And then if we have argon, it's the same thing. The partial pressure of argon, or in this case, the pressure of argon, is going to be equal to the number of moles of argon gas times the ideal gas law constant times the pressure of the argon gas divided by the volume of the argon gas. And so here we have two different equations for the pressure of neon and argon gas. Now, if we mix these together and they're in the same volume and they're under the same temperature, then what we can do is we can find the total pressure of the gas in this container, of the mixture of gases in this container, by writing, we have the pressure total is going to be equal to the partial pressure of the two gases. So the total pressure is equal to the partial pressure of neon plus the partial pressure of argon. So if we write that out here, I'll write that out here. So the total pressure is going to be equal to the partial pressure of neon plus the partial pressure of argon. So then this goes here. So now we just substitute these expressions. I substitute this in and this in for the partial pressure. So then I get the total pressure is equal to the number of moles of neon multiplied by R, multiplied by the temperature of neon, divided by the volume of neon, plus, and then the partial pressure of argon, written as the number of moles of argon multiplied by the R value, multiplied by the temperature of argon, divided by the volume of argon. So now I have the total pressure inside my container here is equal to these two expressions here. Now, the interesting thing about this is, well, we know since they're in the same container and the volume, the particles are mixed together inside the same container. So therefore, the volume of the gases has to be the same. So the volume of neon has to equal to the volume of argon. So we can just call that V for volume. And therefore, since they're mixed together in the same container, they've got to have the same temperature. So therefore, the temperature of neon is equal to the temperature of argon, which is just going to be equal to T. So whatever the temperature is. So we can then substitute in T and V for these expressions. So Tn, Tne, and Tar are going to be the same. Vne and Var are going to be the same. So then we just have the total pressure is equal to the number of moles of neon multiplied by RT divided by V, plus the number of moles of argon multiplied by RT divided by V. So since RT and V are the same, we can combine those together. So then we take out the NAR and the number of moles of neon and the number of moles of AR, pull that out. So now we have the sum of the two moles, the sum of the moles of neon plus the argon moles multiplied by RT over V. What does that give us? It gives us this equation here. So the total pressure is going to be equal to the total number of moles of all the gases mixed together multiplied by RT over V. So here we have Dalton's law written in the form of the ideal gas law. So you can use the ideal gas law to help you find the total pressure if you know the total number of moles of all the gases. So if I know the number of moles of this gas here, and I know the total number of moles of this gas here, and I know the temperature and the volume, then I can use the ideal gas law here, plug in, calculate what the total number of moles are, and then multiply by the R value, temperature, and volume, and then that'll give me the total pressure. Or if I know the total pressure and I know R, T, and V, then I can solve for the total number of moles. So either way, I have this form of the equation of finding the total pressure using the ideal gas law. So that's it for this video. I hope you enjoyed this video. I hope this was helpful. If it was helpful, if you did enjoy this video, then please like the video, share the video. Also hit the like button somewhere over there. If you also make sure you subscribe to my channel, hit that notification bell. Make sure that when you do, make sure you click all so you are notified by all the videos I put out. And then finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have any topics you want me to cover, if you have a question or a problem you would like help on, I would love to help you with that. Thanks for joining me and have a great day.